Hi, and welcome to the 3.07 Intermolecular Forces teaching session video. These are the Common Core standards that we are addressing with this lesson. The previous material that we absolutely need to have mastered in order to do this lesson is Lewis dot structures. You must be able to draw Lewis dot structures in order to do 307, so please, if you have not mastered 306 and drawing Lewis dot structures, please go back to that lesson, as that's where you will find the instructions on how to draw your Lewis dot structures. So, in 307, we see valence shell electron pair repulsion theory. That's what VSEPR stands for. And basically what that means is that, yes, we have our Lewis dot structure for our molecules, but those valence electrons that are around the central atom, they're going to repel each other. And if those electrons are in a bond, they're going to repel each other a little bit differently than if they're not in a bond, or what we call non-bonding or lone pair of electrons. So we must have our Lewis dot structure. We have to identify our central atom. And for the central atom, we have to be able to identify how many lone pairs of electrons are on that central atom and how many bonds are on that central atom. And from that information, we're going to be able to figure out what the true molecular geometry is for that molecule. There are 7 basic classifications that we cover in this course. Now, if you're a student who likes to Google a lot of things, you will find a lot more than 7. However, for this course, we're only going to worry about the 7 most basic classifications. So the first one we have is what we call linear. Linear is where you have 2 atoms. Okay, so these spheres represent the atoms. So we have 2 atoms, so there really is no central atom because there's only 2. So if you have 2 atoms bonded together, such as H2, they have to be in a linear fashion. So their bond angle is going to be 180 degrees. Now let's say you have one atom in the center, okay, one central atom, 2 atoms bonded to it, and the central atom does not have any lone pairs of electrons. And what that means is when you draw the Lewis dot structure, we have one central atom, 2 atoms bonded to it, and if we look at the central atom, there are no dots. Okay, there's no lone pairs. Then it will be in a linear fashion. It's still going to be linear, just like our first one. Okay, our third basic classification is what we call trigonal planar. Trigonal planar is when you have a total of 4 atoms. One of them is the central atom. And when you look at the central atom, there are no lone pairs of electrons. Okay, so that means everything around the central atom is a bond, and is bonded to 3 atoms. The fourth classification is what we call a trigonal planar with 3 substituents. This one is very similar. It has one central atom and only 2 atoms bonded to it. Alright, so there's a total of 3 atoms in this molecule, and then there is a lone pair of electrons. Notice how this looked pretty similar to our last structure, didn't it? Our last structure just had an atom here instead of a lone pair of electrons. And so our bond angles are still 120 for between these 2 atoms. But then this non-bonding pair of electrons, it has strong repulsion. It actually is going to take up more space than an actual atom with a bond. And so that's why we see this big space right here, because these non-bonding electrons are not confined to a particular space like a bond is. So these electrons are able to repel each other a little bit more, and overall it will push these bonds down. Now please keep in mind, you are looking at a molecule on a 2-dimensional surface, whereas molecules are really 3-dimensional, and they're constantly moving in space, so at any given time this molecule is floating around, flipping around, and everything. Okay, the next basic classification we see is tetrahedral. Tetrahedral is the molecular geometry we see when we have a total of 5 atoms. We have one central atom, and then we have 4 atoms bonded to it. Okay, so the blue is our central atom, and then we have 1, 2, 3, 4 atoms bonded to it. All right, and when we look at our central atom, we see that we have 1, 2, 3, 4 bonds, and we have 0 lone pairs of electrons. Remember, your lone pair of electrons is where you see the 2 dots. And for this molecule, there are no dots, therefore no lone pairs of electrons. And we'll get the tetrahedral molecule geometry. All right, the next one we see is what we call trigonal pyramidal. Trigonal pyramidal is where we have 4 atoms again. However, we have 1 non-bonding pairs of electron on the central atom. Notice that everything is about that central atom. That is where the molecular geometry is determined, at the central atom. So we look at our central atom, we see how many atoms are bonded to it. So we have 1, 2, 3. We have 1 non-bonding pair of electrons. So anytime you see that, we see that we're going to have trigonal pyramidal, and the space in between these atoms is going to be a little less than 109.5 degrees. All right, the next one we see is our bent. Pretty scientific, huh? You gotta love it when we have those high scientific words. We actually just call this bent. A bent molecule is one in which we see 3 atoms, only 3 atoms. One of the atoms is going to be the central atom, and then we have 2 atoms bonded to it. And then when we look at that central atom, okay, we have 2 atoms bonded to it, and we have 2 pairs of electrons. So we have 2 lone pairs of the electrons on the central atom. And remember, those non-bonding electrons, these pairs right here, they occupy a large amount of space. Therefore, they push these side atoms down, and that's why these 2 atoms are closer together. A lot of students would just draw this in a straight line, and that's okay for the Lewis dot structure, but when we apply VSEPR, these bonds are not going to be straight. They're not going to be 180 degrees because these valence electrons, and remember, it's 3-dimensional molecule, so one of these pairs are coming out of the paper and the other pair is going into the plane of the paper. Just think of your X, Y, and Z axes from your algebra class. In your lesson, you will actually see all those pictures and this shortcut table. I highly recommend that you save this table and even print it and place it into your chemistry notebook, as it will come in handy when you're doing the assignment. Alright, so now how we read this table is once you draw your Lewis dot structure, then we're going to look at this table and we're going to go by each column and figure out what you have. So column number 1 says total number of atoms bonded to the central atom. So what you have to do is just find out find out what your central atom is, and then look and determine how many atoms are bonded to it. And notice how there are multiple numbers sometimes. 2, there's 3 of them. So what I recommend is when you're trying to figure out what your molecule geometry is, come over here, highlight all 3 of them, the 2, the 2, the 2, or if you have a molecule that has 3 atoms bonded to it. And then we go to the next column. It says total number of lone pairs on the central atom. And that means total number of lone pairs of electrons. Dots. How many pairs of dots are on that central atom? Of course, this is under the assumption that you have a correct Lewis dot structure. So you really have to be careful with that. Alright, and then we see that if we have 2 atoms bonded to the central atom, and the central atom has 0 lone pairs of electrons, that molecule is going to be linear. And here's a few examples, and the bond angle is going to be 180 degrees between the 2 atoms. Now look down here. If we have 2 atoms bonded to the central atom and 1 pair of electrons that are just on the central atom, okay, 1 lone pair of electrons, our molecule is going to be bent, like SO2. So notice how we can get different shapes based upon how many atoms are bonded to the central atom and how many lone pairs of electrons are on that central atom. And that's how you use this table. So just start with this first column, find the ones that apply to your particular chemical. If more than one does, that's okay, just highlight it. Go on to the next column, figure out how many lone pairs of electrons are on that central atom, and then you will be able to figure out the correct geometry for your molecule. We will be practicing that. So we are going to move on to electronegativity values. Probably one of the easiest parts of 307. Electronegativity basically just tells us how much an electron, or excuse me, how much an atom wants its electron. The greater the electronegativity value, such as fluorine has a 4.0, the more or the greater it's going to hold on to its electron. In fact, it's going to hog the electron. Because we're talking about covalent bonds here, and we know that covalent bonds exist between nonmetals, okay, nonmetal bonding to nonmetal. And in that covalent bond, that means that the electrons are shared. Well, sometimes they're not shared perfectly. Have you ever had a case where you and a friend were quote-unquote sharing something, but they kind of kept it most of the time? Well, that's what we call polar bonds. That's where one element is kind of being an electron hog, and they're like, well, I'm sharing this with you, so we're a covalent bond, but I'm going to keep it to me a little bit more. So they're hogging it a little bit more. So it's technically a covalent bond, but it's an uneven distribution. And so what we can look at with electronegativity values is, let's say fluorine is bonded next to oxygen. Well, their electronegativity difference is not that great. Fluorine has an electronegativity value of 4, oxygen has an electronegativity value of 3.5. So if we subtract them, we get a 0.5, so their difference isn't that great. So that means that they're both pretty equally hoggy, if you will. They both want to pull that electron to them. So when these two participate in a bond, it's going to be pretty even. It's not really going to be polar, and that's what we call a nonpolar bond. But let's say fluorine is in a bond with hydrogen over here. Hydrogen has an electronegativity value of 2.1. Fluorine has an electronegativity value of 4. That is greater than 1, and the difference, when you subtract the difference, okay, so 4.0 minus 2.1, that's greater than 1. That's when you start getting into your polar bond region. Okay, it's not an exact black and white answer. Sometimes you can have polar bonds a little bit less and definitely a lot more, but around an electronegativity difference of 1, that's usually where the polar bond comes into play. Alright, so we are going to need to use this table. This is completely out of your lesson. I recommend that you print it because you will need it for the rest of this video and of course for your assignment in future lessons. Electronegativity problem number 1. I would like for you to pause this recording and go ahead and calculate the electronegativity difference between the atoms of HCN. So that means for every bond, calculate that electronegativity difference. And pause this recording, and when you're ready to resume, go ahead and hit play. Welcome back. We have HCN. We're going to have hydrogen bonded to carbon. We're going to have carbon bonded to nitrogen. And it doesn't matter what kind of bond, if it's single bond, double bond, triple bond, it doesn't matter. All we need to know is what the bond is. Alright, so when we look at the bonds, hydrogen to carbon, so hydrogen, and with electronegativity difference, all we need is the difference. So it's the big number minus the small number. So the electronegativity difference between hydrogen and carbon is 0.4. For carbon to hydrogen, we see, carbon to nitrogen. And again, it doesn't matter, negative, positive, so it's just large number minus small number. So we see that value is 0.5. And that's the electronegativity difference. Now we're going to determine the polarity. Polarity is probably the hardest thing in this lesson because it's not necessarily black and white, and that always makes things a little bit hard. It would be great if we could just say if this and this and this happens, it's polar. if you don't see this, you don't see this, you don't see this, it's nonpolar. Not quite that easy. However, we're going to make it almost that easy. The first thing you want to do when you're trying to predict if your overall molecule is polar, okay, what that means is that one side of your molecule is uneven from the other side in terms of electrons, and not necessarily the number of electrons, but how they're being pulled. Remember that electronegativity difference. That has a big deal in this. If your molecule is uneven in terms of pull, it's going to cause it to be polar, which means one side might be a little bit more negative because it has a higher concentration of electrons being pulled towards it, which leaves another side of the molecule being kind of positive because it's missing those electrons. So we get semi-charges, not a real charge. We're not actually giving and taking electrons away. So it's not completely a negative charge or completely a positive charge, but it just a little bit. It's like almost there. So in order for us to determine if something is polar, there are 4 things that we can look at. And then between looking at all 4, we'll get an idea if our molecule is polar or nonpolar. The first thing we want to do is absolutely draw your Lewis dot structure. You have to have that Lewis dot structure, and then you want to correct the Lewis dot structure using VSEPR, which means you draw your Lewis dot structure, you go to that table and you look up, how many atoms are bonded to your central atom, how many non-bonding electrons do you have on that central atom, and then figure out what that geometry is. Then we want to look at the overall symmetry of your molecule. If you were to cut your molecule in half, long ways and sideways, is it pretty symmetrical? Is it asymmetrical? What's going on with the symmetry of your molecule? Then we're going to look at the electronegativity differences in those bonds. At about 1 and greater, okay, so once we subtract the electronegativity, we just did 2 problems, then it's probably going to be a polar bond. Not a polar molecule necessarily, so I want to make sure that's apparent. A polar bond. So we can look at the different bonds and see how the bonds are, and then we have to look at the overall symmetry of your molecule. The last thing we can do, and this might be a short, easy one to do as well, is if you look at the central atom, if there are no lone pairs of electrons on that central atom, and if all the bonds to the central atom are the same, the molecule is going to be nonpolar. So that's a pretty easy way to figure out if it's nonpolar. If the central atom has at least 1 polar bond, remember how to tell what polar bonds are, and if the groups bonded to the central atom are not all identical, the molecule is probably polar. Now we have to be very careful with the second part, because probably polar, there are situations where you can have 2 polar bonds or 1 polar bond and the groups are not all identical, and just because of the symmetry it is nonpolar. So you have to be very careful. So it's really good to use this to figure out if it's nonpolar, and then if it's not this, chances are pretty good it's going to be polar. So it's a good, easy way to narrow down your options. And I know right now you're probably thinking, oh my gosh, that is so confusing. I don't even know what to do. That's okay. We're going to go through a couple of problems, and then it's going to make so much more sense. So what we need to do is figure out, is HCN polar or nonpolar? The first thing we're going to do is draw the Lewis dot structure and apply VSEPR. So go ahead and pause this recording, get out all of your notes that you have so far, your table of electronegativity values, you need your table for your VSEPR shortcut, and you need that slide from the last screen. So definitely get that out, rewind this recording if you need to, do the best that you can to try to predict whether or not HCN is polar, and try to explain why you decided polar or nonpolar. Again, you may have heard me say in other recordings, you really have to try these for yourself. Just watching me do these problems does not mean that you're actually learning the problems. Just as if I were going to watch somebody play the piano, that doesn't really mean that I can sit there and watch them play the piano for 2 hours, sit down, and I can play. Not at all. So that's kind of the same thing here. You have to make sure that you're doing these problems, that you're trying these problems on your own. And then once you get done, or you get as far as you can, then hit play and we're going to work through it together. All right, let's go ahead and start this problem. So we have hydrogen, carbon, and nitrogen. Now remember what I said before. To draw the Lewis dot structure, the first element is usually the central atom. However, hydrogen is never the central atom. Therefore, we go to the next element, so that's carbon. So carbon is going to be our central atom. We're going to start with carbon. Carbon is in group 4, so we're going to draw 4 valence electrons, 4 dots. I see hydrogen, I see nitrogen, and just to make it easy on myself, I'm going to go ahead and just kind of write it how the formula looks. I'm going to start there. So hydrogen I know has 1 valence electron, nitrogen has 5 valence electrons, and I'm going to orient that second, that pair of electrons away from carbon. And now every time that I see 2 electrons, I can join them using a line. And now when I look at this, I say, okay, hydrogen has 2 electrons around it. Carbon has 1, 2, 3, 4, 5, 6. Carbon needs 2 more. Nitrogen has 1, 2, 3, 4, 5, 6. Nitrogen has 6. Well, look at these 2 electrons, and guess what happens? They're going to actually form a bond. So what we get is hydrogen, carbon with a triple bond to nitrogen. And so this is our correct Lewis dot structure. And now what we need to do is look at VSEPR, and we need to identify what the shape is just to make sure that we've drawn it correctly. So we look at our central atom. Our central atom has 2 atoms bonded to it. Okay, so it has 2 atoms bonded, and it has 0 lone pairs of electrons on it. Okay, so remember, this is all about the central atom. Alright, so that's all about the central atom, which is carbon. Has 2 atoms bonded to it, the nitrogen and the hydrogen, and 0 lone pairs of electrons. So therefore, when we look up on that VSEPR table, we see that this molecule is actually linear, and the bond angles are 180 degrees. So that means the angle between hydrogen and nitrogen is 180 degrees, which we knew that because a linear is a line. Okay, so that's our VSEPR, so it's linear, and so now we want to look at the symmetry of our molecule. Is it very symmetrical? Well, I'm not really seeing anything that's symmetrical here, are we? It's not the same on one side to the other. And so when we look at our individual bonds, we can go from carbon to hydrogen, and then carbon to nitrogen. Okay, carbon has a value of 2.5, hydrogen has an electronegativity value of 2.1. Carbon and nitrogen, again, not that big of a difference, 3.0 minus 2.5, so that's 0.5. Neither molecule is very polar, so that's good. And so when we look at this, we go, okay, well, not too bad, not too bad. We look at the central atom and we see, okay, are there no lone pairs of electrons, and are all the bonds even? No, all the bonds are not even. All right, and then it says, do we have at least one polar bond and all the bonds different? Well, the bonds are different. We're not very even, and so is this polar or non-polar? And if you thought that this molecule is polar, you are correct. And the primary reason is that, look at this molecule. We have 1 single bond to hydrogen and 3 bonds, the triple bond to nitrogen. That is going to cause all the electrons to kind of pull towards nitrogen, which leaves hydrogen to be slightly positive. Notice this weird shaped S that I'm drawing? that weird shaped S, kind of like a cursive S almost with a negative, that means a partial negative because the electrons are being drawn more this side, which leaves this side a little bit positive, and we get a polar molecule. How about pH 3? Is pH 3 polar or nonpolar? Go ahead and draw your Lewis dot structure, apply VSEPR, look at the symmetry of the molecule, look at the central atom and see if there's any lone pairs of electrons and if all the bonds are exactly the same, and try your best to figure out if it's polar or nonpolar with a quick explanation. And then when you're ready to resume, go ahead and hit play. Welcome back. pH 3, we've already drawn the molecule, so I'm going to go ahead and refresh our memories. Notice how I'm drawing it a little bit different. It doesn't matter if your hydrogens are left, right, bottom, or if they're at the top, as long as you have the one non-bonding electron pair there. So when we look at our central atom, we see that we have one lone pair of electrons. We have 3 atoms bonded to our central atom. And so when we look it up in our table, we see 3 atoms with one lone pair. We see this is going to be trigonal pyramidal. Alright, and what that means is that these hydrogen bonds are actually just a little bit down. They're not quite 180 degrees between them. So these hydrogen bonds should actually be drawn kind of down here on like angles like this, because one's going out of the plane of the page and one's going into the plane of the page. Again, very hard to draw 3-dimensional atoms on a 2-dimensional screen. You can see the picture of the trigonal pyramidal in the notes in the lesson as well as at the beginning of this recording. Alright, so now we have trigonal pyramidal. When we look at our symmetry, is this pretty symmetrical? No, not too symmetrical, is it? It's really not that symmetrical, so that's not good. And then we want to look at the central atom. Do we have the exact same bonds? And do we have no lone pairs of electrons? And of course, we do have one lone pair, and our bonds are the same, aren't they? It's hydrogen bonded to the phosphorus. It is absolutely the same, isn't it? When we look over it, but it is not a symmetrical molecule, is it? Even though the bonds are the same, we have this non-pair, this lone pair of non-bonding electrons. What do we get with this? This is definitely going to be a polar molecule. Overall, not very symmetrical. We have these non-bonding electrons up here, which is going to change how this molecule behaves. The next topic we're going to discuss is 4 intermolecular forces. Intermolecular forces are those forces between compounds. Let's say that you had water. From VSEPR, we know that water has this molecular geometry. And intermolecular force is how one molecule of water is attracted to another molecule of water. Okay, this force in between the 2 molecules, that's what an intermolecular force is. Some molecules are attracted to other molecules in solution. Some molecules are not. And depending on the type of molecule we have, that will tell us what type of intermolecular force we have. Some of these are stronger than others. The stronger the intermolecular force, the higher the boiling point. Because remember, boiling is when we separate molecules from each other. So we have to get this water molecule away from this water molecule. So the stronger the intermolecular force, the higher the boiling point. Now, when we're trying to figure out which intermolecular force your chemical has, it is best to start with hydrogen bonding, and we can eliminate as we go left to right. Hydrogen bonding is very quick and easy to either say yes, the molecule has it, or no, the molecule does not have it. Hydrogen bonding is basically when your molecule has nitrogen, oxygen, or fluorine directly bonded to hydrogen. Directly bonded to hydrogen. Not that it has nitrogen and oxygen and fluorine and hydrogen, but that they are actually bonded together. Okay, the fluorine has a line drawn to the hydrogen. So in a molecule, it's very quick and easy from the Lewis dot structure to say yes, we have hydrogen bonding, or no, we do not. And on a side note, just because you have a hydrogen does not mean that you have hydrogen bonding. Okay, once again, I cannot stress enough. Nitrogen, oxygen, or fluorine directly bonded to hydrogen. Then we can go to ion dipole. Ion dipole really has to do with solutions. Ion dipole is when we have an ionic compound in a solution. So we would have, let's say, NaCl being dissolved in water, or KCl dissolved in water, or some type of solution. So that is very quick and easy to eliminate, because if you don't have an ionic bond in water or solution, you don't have ion dipole. Dipole really is for your polar molecules. That is a quick, short way. If you can identify if you have a polar molecule, it's going to experience dipole-dipole interactions. And basically what that means is in your polar molecule, one side's going to have that partial positive and one side's going to have that partial negative. Well, guess what? The partial positive of one is going to attract the partial negative of another, because opposites attract. And that's why polar molecules have our dipole-dipole. Your dipole means that partial charge, which is polar. So all those words go hand in hand. London dispersion forces basically is reserved for your non-polar molecules. Even though, yes, it does exist between all molecules. Every molecule in the world experiences London dispersion. But for non-polar molecules, this is the only intermolecular force. If you have a chemical that experiences hydrogen bonding, it is extremely strong. It's not even worth mentioning London dispersion. So what you want to do is you want to list the strongest intermolecular force that your chemical experiences. For example, let's look at water, H2O. So when we look at water, we see that oxygen is directly bonded to hydrogen. Therefore, water does experience hydrogen bonding. Now, does water experience London dispersion forces also? Yes, it does. However, since water experiences hydrogen bonding, it doesn't even matter that London dispersion is there. It is so weak, it's almost as if it doesn't exist, because it's so little compared to hydrogen bonding. Alright, so the strongest force that it has, that's what you're going to list. So if I were on a quiz or worksheet or assignment and I had water and it asked me what the intermolecular force is, I would report hydrogen bonding, and that's it. Determine the intermolecular force of a couple of compounds. It is easier if you determine if the molecule is polar first, because that polarity really helps when you get down to dipole-dipole or London dispersion. Which intermolecular force does HCN, which is hydrogen cyanide, which intermolecular force does HCN experience? Please go ahead, pause this recording, try your best to figure out which one it has, and when you're ready to resume, hit play. Welcome back. HCN, we already drew the Lewis dot structure. We found that this is the Lewis dot structure. Is hydrogen directly bonded to nitrogen, oxygen, or fluorine? No, absolutely not. Nitrogen is not directly bonded to hydrogen. Therefore, it is not hydrogen bonding. Okay, so we can eliminate hydrogen bond. So it is not hydrogen bond. Is this ion dipole? Again, ion dipole is where you have an ionic compound in a solution. Well, this question is just asking about HCN. Therefore, it is not ion dipole. And now what we have to figure out is this dipole-dipole or London dispersion? And remember, that comes down to whether or not we say this is polar. And do you remember if this molecule was polar or not? And yes, HCN is polar. So HCN is polar. Since it is polar, it's going to experience dipole-dipole intermolecular forces. Go ahead, hit pause on your recording so that way you can work this problem out at home, and when you're ready to resume, hit play. pH 3, we already drew the Lewis dot structure to this twice, so I'm going to go ahead and draw it here. We want to see which intermolecular force pH 3 experiences. So we have to look and see, does hydrogen form a bond to either nitrogen, oxygen, or fluorine? We don't even have any of those, so it is definitely not hydrogen bonding. So we know that for sure. Ion dipole. Is this an ionic bond in a solution? Absolutely not. So it is not ion dipole. Then our decision is if it's polar. So we have to look at it if it's polar. And remember from the slide before, we've already figured that out. And yes, this is polar, therefore this experiences dipole-dipole interactions. This slide I put in here, even though this lesson does not really talk about what is ionic or covalent bond, because that was a previous lesson. This is needed for the assignment, so I wanted to throw it in here, that way you are very prepared to do that assignment. In the assignment, you are asked to classify all your compounds as ionic or covalent compounds. Remember that an ionic compound is anytime we have a metal bonded to a nonmetal. Covalent bonds consist of all nonmetals. Thank you so much for joining me.